Okay, let's get started. So today I'm going to cover Go routines. And Go routines are Go's abstraction of running code in essentially conceptually in parallel. So let's say you have a 2 gigahertz processor with say 4 execution units, or we call cores. Conceptually, you could run 4 instructions at the same time. And Go allows you to parallelize your code or have your code run simultaneously, possibly through the um, use of Go routines. So a Go routine basically starts an independent execution of code. This isn't to say that having 4 execution units or cores on a 2 gigahertz processor is like having an 8 gigahertz processor. It isn't. Um, those cores share some resources, and there are points in your program where you kind of serialize your access to some data. Maybe they all need to share some common files or something. But anyway, it's not exactly the same thing. And the drop off is even worse with hyperthreading, where you run multiple execution units within a core. And a lot of times, hyperthreading only gives you about a 30% burst, even though it doubles a 30% performance increase, even though it effectively doubles the number of execution units. There's just too much contention at that point. So let's start with uh, Go routines in general. So the way you run a Go routine is you use Go and then the function invocation. So let's try to run something fast in parallel. Log, and we'll log the end of the program here. Uh, Good. Okay. So let's open a terminal and go run. Okay. Well, here's the thing. We never saw the text something fast come out. So we're running our code. We print our log statement hello world. Great. We see that here. We run something fast in a Go routine, which basically is telling Go, hey, run this possibly at the same time, but you decide when you're going to run this, but run this conceptually at least concurrently with this code. And then we have our goodbye statement, but we never see the output from this statement. So what's going on? Well, when I said that Go runs these things in parallel, that's not quite totally true. So Go routines are not uh, full heavyweight system threads, which will always execute in parallel. They're very similar to something called a coroutine. That's co with a C as opposed to go routine with a G. So coroutine is essentially a way to write some code, and even if you can't run it at the same time as other pieces of code, uh, physically, I mean, the processor, maybe you only have a little one core processor and it can only do one instruction at a time. Even though you can't run them at the same physical time, you can logically run them at the same time. So over, say, a second, each coroutine makes some progress. Goroutines are a cross between that and full threads, because a coroutine may or may not get scheduled to run at the same time as the main thread or the main go routine. So what's going on? So here we're actually running off the end of main before the scheduler is able to run this. So in order to give the scheduler a chance to run that, we need to stop. So one way we can stop is we could say, okay, let's put in a wait here. So we're going to put in a 2-second wait. That should be long enough for most purposes, right? So we'll say time.sleep 2. second. Okay. So now if we run it, okay, so we see our hello, great. We saw hello, great. We kick off a go routine with something fast. Then we print goodbye, and we see that, right? And then we see the output from our go routine, something fast. Okay. Conceptually, it was running at the same time. It's just that when it got actually scheduled to run, meaning that the Go runtime system decided, okay, it's time to run this code. Main was done, and the sleep, it was only the sleep that allowed something fast to get a chance to run. Unfortunately, there's a problem with sleep. Let's call something slow in addition to something fast. Go something slow. Okay. Now if we run it, we see our hello world. Well, actually, we don't output anything from slow, right? So let's output something from slow. Log println I'm done. Okay. So now we see hello world, right? We see goodbye. Great. When we're done, we see the something fast output, but we don't see the output for something slow. That's because a 2-second delay wasn't sufficient to allow something slow a chance to run, because it's going to, well, it was running, it just waits for 3 seconds. So it main completed before something slow had a chance to complete. So given that we can't play a war of increasing timeouts, what do? Well, the easiest thing to do is create what's called a wait group. So let's create a wait group called WG, and it's in a package called sync, and we're going to add 2 threads to it. And we are going to pass the wait group to the threads. Okay. Now, we've added 2 threads, and when the threads are done, they need to call WG done on the wait group. So they call there. Okay. Actually, let me pop open the documentation for wait groups real quick. There we go. Sync. And here we have wait groups. So there isn't much to a wait group, but so when the running go routine is done, it calls WG done on the wait group. Now, what do I need to do in my program down here? Well, I remove this sleep, this attempt to keep the program running to give the other go routines a chance to complete, and replace it with wg.wait. So what's going to happen here? So I'm going to start, and I'm going to tell the wait group, hey, I'm going to start 2 go routines. And I start the 2 go routines, and I come here to, actually, let's put the wait group in front of the goodbye, because that's what we really want to do, is we want our program to say goodbye as the last thing, right? So we're going to start these 2 go routines, then we're going to wait. So until we get 2 calls to done on that wait group, so we're expecting 2, we told it to expect 2. Until we get 2 calls to done, we're going to wait here for the other stuff to complete. So let's go ahead and run this. And so we see hello world, we see something fast. Oh, why was there a deadlock? There should be no deadlock there. There should be no deadlock there. I need to pass a pointer to a wait group. Okay, that's it. I was passing a copy of the wait group, not a reference to the wait group. So I create the wait group, and if I don't pass a reference to the wait group or a pointer to the wait group, what I do is I get a copy of the data in the wait group as opposed to sharing the wait group. Normally I don't worry about this because I do wait groups in Clojure, so I don't actually usually pass them as arguments. But anyway, long story short, you need to pass them, as you can see, as a reference to your method. And we get what we expect. We say, hello world, we get something fast, and then we get the slow saying I'm done. And then once everything that we wanted to run is done, we can go ahead and leave the program, right? Fantastic. Wait groups are fine. There's nothing wrong with wait groups. But sometimes you need to share something with a program. So you need to share some data. You need to say you want to uh, tell something fast or something slow what to print. Another way, so let's get rid of our wait groups now that we're done with a wait group exposition, is we can send messages to channels. So in a lot of languages, when you want to share data between two systems, you basically have some primitives that say, hey, only one thread of execution can be in this section of code at one time. And there's a tendency for us to get those wrong because it's hard to do. And by the way, if you haven't already guessed, um, Goroutines are what I call a sharp tool. A sharp tool, if you're not used to that metaphor, is a tool that can do amazing things, but also carries a certain amount of danger with it. Now, it's not like it's going to cause your computer to blow up or anything, but it can be really frustrating and difficult to debug issues where you have concurrency or code running at the same time. So in this case, what I'll do is I will create a channel, and I will create a string channel. So I will call this fast chan, and that will be make chan string and slow chan. So I'm going to create two channels, and I'm going to pass them to the methods. Okay, and slow chan. And what I'm going to do is I'm going to I'm going to use that channel to send the text that I'm going to do. And then what I'm also going to do is I am going to say, uh, what, yeah, what's the red squigglies for? Oh, duh. Okay. All right. So what I'm going to do is I'm going to say, okay, I'm going to wait for a string. That's going to be my message. I'm going to print that message. And then on the same channel, I'm going to send back a done message. And we'll do the same thing here. Now, what I'll do is I'll say, ask Chan. I'll send it the message, something fast and slow. Well, let's make it different. Something fast too. I really need to do that after I start the Go routines. I really can't do it before then. So let's do it down here. Okay. Now, I'm going to wait for the messages. So I'm going to say, uh, okay. So what am I doing here? So I'm creating two channels so I can communicate with my programs. I'm passing those channels to my subroutines. I'm sorry, I call them programs, but subroutines or functions. And then I'm sending data on those channels. Now my functions are going to wait for some data on the channel. That means they're going to stop here until data arrives. They're going to print their data, and then they're going to send back the message done on that same channel. Same thing here. Something slow is going to listen for data coming in on a channel, and this arrow operator means I'm going to take data from the channel and put it in this variable. Then I'm going to sleep, I'm going to print the message, and then, and again, this arrow means I'm taking this piece of data and sending it to the channel. So what's going to happen is, this is going to run, it's going to start my Go routines, I'm going to send some data to the channels, and then I'm going to wait for some data. So if we go run this, we see our behavior, right? So um, we see that we waited until we got the responses back from the channels, and we didn't have to worry about main completing before our other two routines. Okay, now there's a problem with this. So if I go here and I say, okay, start my Go routine, I pass the channel, I start my slow Go routine, I pass the slow channel, I send them some data, okay, that's fine. But then down here, I wait for slow routine first and the fast one later. So that means my program is going to stay around, and I'm going to, whatever memory could have been released with something fast finishing has to sit and be held until that done message can be picked up. And since slow is going to take forever to get its done message done, I'm going to have that memory just sitting around held by whatever is in something fast, right? So ought to be a better way to do this. And there is. We have what's called the select statement. And we can say, so I don't use select too much. So I think this is case. And this would be case as well. And what we'll do is we'll keep another item number here. So we'll do done. Let's do this for I equals 0, I less than 2, plus plus. So we'll repeat this loop twice. Okay. So we'll repeat this loop twice. We'll wait for data from the slow channel, we'll wait for data from the fast channel. Okay, and here we see the output. We see our hello world, great. We see something fast did its work, and then fast is done. That's right. So fast was able to clean up, and then we waited for something slow, and slow is done. We got that message, and we were able to clean that up and continue on. Now, what's going on here? So um, select is going to wait until there's data coming from either fast chan or slow chan. So we're going to wait for one of these two to arrive with data. Now it turns out that fast chan is going to be the first one to deliver data. So it's going to execute this code, and then it's going to go back and loop once again, and we're going to hit the select statement again. Now, we're never going to get data back from fast chan, right? So we're going to get data back from slow chan at this point, and that's all we're waiting for. And then we're done. We've gotten 2 responses. That's what we're expecting. We clean up and we're done. Okay. That is how both you could implement waiting for something to complete and how to pass data to a go routine. Now it could be that, for example, something you could have a file copy where you run one go routine to read the data from one of the files, and you have another go routine that writes the data to a file. And you pass data back and forth using these channels to kind of allow the reading to happen and the writing to happen independently. And now that's important because I have a 3-second wait here on slow channel. So slow channel is going to take 3 seconds. But in reality, most applications, especially web applications, have to wait a long time for input or output. Now you may think, oh, the file reading and writing happens almost instantaneously, but that's really not the case. Files take several milliseconds to read and write off spinning hard drives or off a network hard drive. So for example, if you're reading or writing a file from a network location, it could take several milliseconds to access that data. The instructions inside your computer are running on the order of nanoseconds. And that's a million times faster than the speed at which you can bring data back off the network. So because of that, a lot of programs like web servers and file copy routines and so forth, they're actually bound not on the computation side. Like a video game, video games are bound. Where a video game spends all its time is furiously using the GPU to render a scene. It's doing computation constantly. But something like a web server is basically spending most of its lifetime waiting for input or output. So if we put in those reads and writes in separate Go routines, we could have a situation where, okay, fine, we're waiting to read data. Okay, but fine, we're also waiting to write data. But while we're waiting to write data, if data is available, we should go ahead and read it. Likewise, if we get ready to write data, we should go ahead and write it. Um, okay. One of the things to watch out for with channels and Go routines is that Go will usually detect it. They'll detect some sort of a deadlock situation, um, but they won't detect everything. So you can start your program and just sit and drum your fingers while the program does nothing. Okay. I do want to cover one more type of actually, I'm going to cover range statements first. So let me create another channel. Uh, let's call it chatty. And we're going to pass chatty into something fast. And there we go. So what we're going to do is for I equals, whoop, I equals 1, or I equals 0, I less than 10, I plus plus. Mixing my languages there. So we're going to send chatty, and all right. So we're just going to send some messages. So we got some messages coming in from chatty. We need to process those. Now, I'm not saying that this is the best arrangement of code possible, but you can do so. In this case, we have whoop, don't want that. Anything else I got here? Nope, just the two. Okay. Now let's do a printf. It's not happy. Why is that a room? All right, let's try it and see what happens. Ooh, weird. All right. I don't quite have it right, but long story short, you can do ranges over channels as well. And the interesting thing about a range over a channel is this could be dynamic. So let's say, for example, we could have had up to, thousands of these things, like you were reading or writing from a file. You don't know how long the file is. Um, so you can actually use ranges over channels to read all the data out of the channel, although it didn't do something right, so I'm not sure what I did wrong. Um, okay. Um, well, that's pretty much it for today. I did want to cover the basics of Go routine, and I did want to cover at least some of the synchronization stuff. And just, the one thing I did want to go over, one thing to take away from it though is if you don't synchronize, and I didn't do an example of this, you could easily wind up having one Go routine trash a variable that's being used by another Go routine at the same time. And when that happens, now in my case, I didn't have that issue because I passed everything as a parameter, but sometimes you have shared variables. When that happens, you wind up with buggy code, and it's these bugs are insanely hard to find. Um, so long story short, you can share stuff and you can get in trouble with sharing stuff between Go routines. And I just wanted to set up that notion of things running at the same time and possibly bumping into each other to set up I think the next discussions I'm going to have next week around maybe extending some of the web stuff to include a little bit better fleshed out example than Tuesday's stream. But in order for that stuff to really make sense, I really needed to cover the basics of things that run at the same time, so that you have an understanding of why things are the way they are when we start building out more capable web services. All right, that's it for today. I will see you next week.